So as I mentioned in an earlier video, when we talk about end behavior, what we're talking about is the limit as x goes to infinity of the function, or the limit as x goes to negative infinity of the function. Literally the left and right ends of the function. All right, so we are going to find the behaviors of the following functions. There's that word again, analytically. I know it's your favorite, right? And we're going to sketch a graph for each showing the end behavior and identifying any existing asymptotes. Oh, any existing asymptotes. That's interesting verbiage, because you might be thinking, oh, well, I'm just going to find the horizontal asymptotes. But if you recall, asymptotes could be vertical, horizontal, or oblique. Here, also known as slant asymptotes. So any one of those three is possible. We might have to find them using all of our pre-calculus and everything else. Alrighty, so let's start with the first one. As a matter of fact, I'm going to divide my paper up. So let me just put a line in real quickly. That way I'll hopefully be able to manage keeping the two problems separate. Okay, so we're going to start over here, which is f of x equals 2x plus 1 divided by 3x to the fourth minus 2. And I'm going to divide by the highest power in the denominator. So I'm going to change this function to a slightly different function using some algebra. So I'm going to multiply it by, well, first of all, let me just write this out. I'm going to take the limit as x goes to infinity, either one, and I'm going to take it of this function. So, but I'm going to modify that function. And the way I'm going to modify it is I'm going to multiply by 1 over x to the fourth divided by 1 over x to the fourth. So in other words, I'm multiplying by, well, I'm really dividing by the highest power in the denominator. It's my little trick. Oop, there we go. Okay, so that's modifying the function. So instead of just writing this like this, I mean, I could, but I'm going to be a little craftier about it. So I'm going to write the limit as x goes to infinity. And instead of f of x, I want to write, let's see, 2x plus 1 multiplied by 1 over x to the fourth. So that would be 2x over x to the fourth plus 1 over x to the fourth. I have a plan. Don't worry about that. And then 3x to the fourth times 1 over x to the fourth would be, let me think, 3x to the fourth over x to the fourth, because that's a grouping symbol right there. Oh, I'm so sorry, minus 2 over x to the fourth. Minus 2 over x to the fourth. Okay, well, I know what you're thinking. You're thinking that did not make anything easier. Well, it actually did once you simplify, because you know that, for example, down here, the x to the fourth and the x to the fourth are going to go. You know up here that this x and this x to the fourth are going to make x to the third up here. So you're going to have 2 over x to the third minus 1 over x to the fourth, 3 take away 2 over x to the fourth. Now let's use the fact that we know that when we put a constant and divide it by infinity, we're going to get 0. Right? That was the theorem we just learned on the previous page. Right? So if you take a constant, you take a constant and you divide it by x to the n, when x goes to infinity, you will head to 0. And we learned that it actually is true for any constant k, because actually you would pull the constant out and you'd be fine. So that means that we have 2 over infinity cubed actually, which is 0, minus 1 over infinity, which is 0, over 3, take away 2 over infinity, which is 0. That's 0 over 3, which is 0. Now, there's nothing special about how I did this, right? So I could do it with the other side just as easily. So what I just did right here is the right-hand edge, because I was going towards positive infinity. So this was the right end of this graph, because I'm heading to positive infinity. But I can do the exact same thing with the left side, and actually I don't even need this middleman step because I already know how it's going to work because it's the same function. So I'm going to do the same thing. I'm going to use this part right here, but I'll do it in green, and I'll say, hey, for the left edge, do the same thing, but take the limit as x goes to negative infinity of 2 over x cubed minus 1 over x to the fourth, 3 minus 2 over x to the fourth. Okay, but that's still 0. Take away 0 over 3 minus 0. Nothing changes in this one. Some of them, they will change, but this is not one of them. So I'm heading 0 over there too. And these two things together mean that I have a horizontal asymptote at y equals 0. As a matter of fact, either one of these, just this one alone, meant I knew I had a horizontal asymptote. So I know that I have a horizontal asymptote at y equals 0. Right? Horizontal asymptote at y equals 0. One of my asymptotes is found. Hooray! All right, now there's just one little bit left before I start dealing with any of this, which is the vertical asymptotes. The thing about slant asymptotes is that if you have a horizontal, then you don't have a slant. So since I have a horizontal, then I know I don't have a slant asymptote, so I'm fine there. But I could, and do, in fact, actually have a vertical asymptote. So here's the answer to one part right here, the horizontal asymptote. To find a vertical asymptote, we have to remember our algebra here. I can't spell though. There we go, tote. All right, to find the vertical asymptote, we set the denominator 3x to the fourth minus 2, and we set it equal to 0. And we solve. There's a couple ways you could solve that, but the easiest thing to do is just to add 2 to both sides. So 3x to the fourth equals 2. Then divide by 3, so x to the fourth would be 2/3. That would mean that x is equal to plus or minus the fourth root of 2/3. There we go. So the fourth root, because I had to take the fourth power of both sides. So in other words, I'm saying plus or minus 2/3 to the 1/4 power. That would also work. Now the thing about the plus or minus is because you're doing an even root of both sides. You learn in algebra class that whenever you take an even root, square root's the most common, but whenever you take an even root of both sides, you need a plus or minus. So I put that in there. All right, so now let's see if I am correct. She says knowing that she is correct, but let me prove it to you. All right, so here we are. This is example 3a. Let me pull that up. And here's the function, and you can see that there are the asymptotes. Let me switch to projector mode here real quickly so you can see it a little bit better. So we have vertical asymptotes and we have horizontal asymptote. And the horizontal asymptote is rather obviously y equals 0. I was indeed correct about that. But you can see that I have my vertical asymptotes placed appropriately, and that's because I have them at the 2/3 to the 1/4 power and negative 2/3 to the 1/4 power. And there they are. So indeed, I was correct. And my graph on Desmos is verifying what I said. So I'm going to redraw this graph real quickly on my paper. All right, so I have my scale, of course. I have my graph, lovely. And I can see my two vertical asymptotes at plus or minus 2/3 to the 1/4 power. Right there they are. And that's these ones right here. They're my vertical asymptotes. And then my horizontal asymptote was at y equals 0, which is right here, which is that line right there. Right? So sure enough, it verifies what I said. Now let's look at letter B, and we're going to use the same trick. So we're going to divide by the highest power in the denominator. So the highest power in the denominator is x squared. So I'm going to do 1 over x squared over 1 over x squared. I can do that because I'm putting it over itself. So I'm multiplying by 1, which comes up with an equivalent expression. It's not exactly the same expression, but for all intents and purposes, it's equivalent for what we need. Denominator. Okay, so let's see if we can do this in our head a little bit. So I want the limit as x goes to infinity This will be the right-hand edge I'm doing first. So the limit as x goes to infinity, 3x squared over x squared would just be 3 minus 7 divided by x squared. So you have to distribute that 1 over x squared to both of them. And then down here, I would take x squared over x squared, which is 1, and then 5x over x squared, which would be 5 over x, right? So I'm distributing each one of these, and I'm doing it in my head, right? X squareds cancel for the first term, nothing cancels for the next term. X squareds cancel down here. X squared over x squared makes 1, and then 5x, x goes into x squared, x times. Okay, but remember that this one and this one are going to go to 0, right? So this is going to be 0 and this is going to be 0 as x goes to infinity. So it's going to leave us 3 take away 0 over 1 plus 0. And last time I looked, that was 3. So that means that we have at least one horizontal asymptote at y equals 3. All right, now we have to do it again for the other side. So let's do that in green, right? So this was the right-hand end that I was doing up here. And then the left-hand end is, let's see here, left-hand end limit as x goes to negative infinity, and then it'll be 3 minus 7 over x squared over 1 plus 5 over x. And sure enough, that didn't change anything. So it's 3 minus 0 over 1 plus 0, which is still 3. So that's still my horizontal asymptote. Okay, so I know I have my horizontal asymptote. My vertical asymptotes will be whenever the denominator would be equal to 0. So asymptote. So I would take my denominator of x squared plus 5x. I would set it equal to 0. That factors. So either x is 0 or x is negative 5. So those two are my vertical asymptotes. Or VAs if you want to call them that. All right, so I have vertical asymptotes at 0 and 5, or negative 5, excuse me. And I have horizontal asymptote, a horizontal asymptote at 3. All right, let's see if the graph in Desmos backs me up. All right, so here's the graph right here, and you can see that I do indeed have a horizontal asymptote and 2 vertical asymptotes. And if you want to see them, there they are, 3, 0, and negative 5. And sure enough, it works just like we expect it to. So I would redraw this graph on my paper and label my axes and my asymptotes. And there it is. And I have my axes labeled, my asymptotes labeled. I should have labeled them on this other one and I didn't. So there they are at y equals 0, and then my 2 vertical asymptotes at plus or minus 2/3 to the 1/4. Here I have my asymptotes at 0 and at negative 5. Right, they're my vertical ones. And then I also have my horizontal asymptote at 3. And just on a side note, you'll notice that the end behavior is working out like we said it would. We said that on the left end that we would be heading towards 3, which is right here. There's the left-hand edge, right? And then the right-hand edge is up here. So if I just label this, this is left right here. And then over here, because you're heading to positive infinity, this is the right, which I'll just do in pink right here. Right, so that's the right-hand edge, which is what's happening right here on the graph down here. So you're heading towards positive 3 as you move towards infinity. So the left and the right are indeed working out just like we said it would. And actually that worked on this graph too. I just have the wrong color. All right, so if I make it pink for the right end, then when you look down at the graph, you can see that right here is the pink part. Right, we're heading towards infinity. So there's the right working just like we said it would to 0. And over here is the left going towards 0 as well, just like we said it would right there. So the graph is in fact backing up our horizontal asymptotes, our right end, our left end, and our vertical asymptotes. Everything's coming together.